dx. I'm going to write it that way. And then I'm going to use the power rule. What's the power rule? If this was x to the n, what do you do to this? You add 1 to it, right? Don't you add 1 to this? So it'd be x to the negative p plus 1 plus c. And then don't you have to put a constant out here, like divide out? That same power goes out here. Y'all look stunned. If I do antiderivative of x cubed, the antiderivative is 1/4 x to the 4th. What did you do? You added 1 to the power. You have to scale by that, right? Same thing. I have x to the negative p. What do? I add 1 to the power. I put 1 over negative p plus 1 there, right? So you all okay with that? Okay. Is this defined for every p? There's one p this doesn't work. If p is 1. If p is 1, this doesn't work. So this works so long as p is what? Not 1, right? This is true as long as p is not 1. Because if p is 1, that's division by 0 right there. Right? Okay, so let's run over here real quick. What if p was 1? What is this function? No. 1 over x. Have I shown you what that one does already? What does it do? It diverges. I did that last class. So if p is 1, we already know that diverges, don't we? So I'm going to continue with this formula. We can't use p1 here. That's okay, because I already know what happens when p is 1. Got it? Okay. Okay, come back over here. Equals limit t goes to infinity. All right, bracket. I'm going to write my antiderivative, which is 1 over negative p plus 1, x to the negative p plus 1. And I'm going to evaluate that from 1 to t, not p, right? And remember, I have a big asterisk here now, right? Like p is not 1, p is not 1, p is not 1.
So why are you throwing in there?
What? P is not 1. P is not 1.
Oh, that's right.
Not,
Okay, got
not,
it,
yeah.
got it. Okay.
X can be 1, not p though. Were you? Okay, I'm going to keep going. Limit t goes to infinity. Okay, I have parenthesis minus parenthesis bracket. Okay. What gets plugged in first?
T.
T, and it gets plugged in for what? For x. For x. So this becomes 1 over negative p plus 1. T to the negative p plus 1. So that's what happens when I replace that x with t. And then, let's see, I plug in 1 for x, right?
Yeah.
1 raised to any power is 1, right? 1 to any power is 1. So all you get is this, right? 1 over negative p plus 1. All right? We have one limit to think about here. T is going to go to infinity. This right here is a constant, isn't it? That's just a number, whatever it is. T is going to infinity. So what I'd like to know is what does that do as t goes to infinity? Pause, time out, don't jump too far here. I need room. I think I'm going to erase this. Is that all right? I want to know right now what happens when I do the limit as t gets huge and positive of t raised to the negative p plus 1. So imagine that that gets big, infinitely big, and you're raising it to a power. What happens? Careful. It depends on if this is a positive or a negative number, right? Because if this is a positive number, like 2, then a big number squared would get bigger, right? If this was a big number, or if this was a number like 3, a big number cubed would get bigger. But what if this was negative 2? A big number to a negative 2, you would drop it down, and now it would become 1 over a big number, which would head to 0. So doesn't this dictate what happens? Yes? So I'm going to say that. If the negative p plus 1, as long as it's positive, right? As long as this is a positive number, then a big number raised to a positive number should get huge, right? Then the limit as t goes to infinity of t to the negative p plus 1 should go to infinity. Right?
Yes.
But if that negative p plus 1 is a negative number, right, then that limit's going to go to where?
0.
The limit's going to go to 0. Okay? So come back over here and let's answer this question. What is the limit of this? Well, there's two different cases, right? There's two different cases. The first case is when this is true. What's another way for me to say that? Negative p plus 1 is greater than 0. Move the p to the other side. Add p to both sides. What is that saying? Yeah, 1 greater than p, right? That's this case right here. That's the same as saying 1 greater than p, or p is less than 1, right?
Yeah.
What happens in this case? That limit goes to infinity, and if that limit goes to infinity, this integral diverges. And that's exactly what this is saying right here. Oh, wait a minute. We have an equals there too, right? Because what if p is 1? Well, that was that first case, right? We did 1 over x last class, and that's divergent. So we diverge in any of these cases. And then what if we look at the other way? What if we do this? What's another way I can write that? P is bigger than 1, right? Then that limit goes to where? 0. That goes away, and what am I left with? This, which is a number, right? This is just some number, and which means I'm convergent. I converge to that number, which is this, and I'm done. All right? Like I said, that's not something you would have to show, but it's kind of interesting that you can do that, right? I mean, all right. Type 2, what time is it? 12:15. Our test is on Thursday, right?
Yes.
Okay. Are there any questions on this?
So for this one,
Yeah.
we don't know the answer right now because there could be two outcomes depending on.
Well, what we were trying to do in this is, what we were trying to do with this is for us to show that anytime you have this integral that looks exactly like that the p, the power on the x, will dictate exactly what happens. And if that p is smaller than or equal to 1, I guarantee you we've got divergence. And if the p is bigger than 1, we've got convergence. All we did was showed why it's true. Okay? So now how do we use that? Like if you want to see an example, if I ask you what this is that convergent or divergent? Divergent. Why? What's the p? What's the power on that x? 1/2. That p is less than 1. Less than 1 p means divergence. This is a divergent. I don't have to actually show, I don't have to go through and do a limit. I know that that's a divergent area under there. Does that make a little more sense if I say it that way? Yeah? And what if I did this? 1 to infinity of 1 over, I don't know, x to the 7th dx. That's convergent, right? Now, I'm not able to tell you right away. Well, actually, we had a formula to show what it converges to. But I can tell you right now that that does converge.
So,
All right.
like I know that these are true. It's more than true. So like, when would this would this ever like speed up the process of doing one of these problems per se?
Oh, absolutely. Like I mean, this, in theory, because we've shown this formula in class, like if these come up, you don't have to do any work.
So this is I would say like, so this would probably look like you would split maybe one of the integrals or do something, and then you could just automatically say that this side's infinity. And there are.
Oh, I see what you're saying.
Yeah, I'm trying to imagine how
Let me put it this way. Will this property hold if I do this?
No.
No,
Is that 0 again?
because we start at 0, right? So then maybe you say, I'm going to split it up. I'm going to go from 0 to 1, right? And then I'm going to go from what? 1 to infinity?
Yeah. So then you
And
can
that-
get the right side, like,
That diverges, right? So it doesn't matter what this one does, right? You could do something like that, yes.
okay, because that I was trying to see the use case, but I
Yeah.
I like that.
Uh-huh.
So in this situation, once we get to the points where we can see that the right integral diverges, then the problem's done.
That's it.
Okay.
Yep.
Because
Okay.
I guess even if the other side's negative infinity, it's like, it still diverges.
Yeah. Let me ask y'all something. What if I used a different number here? Like instead of 1, what if I picked a number to the right of 1? No, to the right of 1. So instead of this formula, 1 to infinity, what if I do k to infinity of 1 over x to the p dx, and I tell you that k must be greater than or equal to 1? What do you think? Do you think this still holds?
Yes.
You think so?
Yeah.
Let's think about what this is saying. We have some function at 1 at something, and then we know it dives down to 0. The area here, if this p is less than 1, this area is infinite. If less than or equal to 1, if this p is greater than 1, then this is going to be a finite area, right? That's what we know so far from this. What I'm saying is, what if you take a point to the right of 1, k, and you talk about this area instead? So what if I told you that the blue area was divergent, that it became infinite? What could you tell me about the red area? It's the same. Why? Convince me. If the blue area was infinite, why can you tell me the red area is as well? Go ahead.
Isn't it because the red area falls in with the blue area?
Yes, but it's less. Do you agree there's less area in the red than the blue? So I think you're understanding, but I think what you're saying is not. You want to try and rephrase? Let me ask you this. If the blue is infinite, right? The blue area is infinite, and I say, hey, take this much out. Would you agree that that area is finite? So you have an infinite area, and you come and carve out a finite amount. Don't you still have an infinite area?
Yeah.
That's the idea.
So it's the end behavior, I guess you could say.
Well, the infinity is coming from what's out here. Is from wherever point you are out, that's the part that's infinite. The infinite part is not coming from this finite piece from here to here, right? Because the integral from here to here is just a number.
So this works from
K to infinity as long as k is bigger than 1.
okay.
As long as k is bigger than 1. That's the power. That's something else. Yeah. I know I'm getting confusing things. Now, let me ask you the other way. What if I tell you that the blue area was finite? That the blue under here was a finite number? Would the red area still be finite?
Yes.
Yeah, because you're taking out how much? A finite amount from a finite amount, and you should still have a finite amount. So this property, you could generalize it even more and go from k to infinity. But I think, in a textbook, they don't want like all these damn variables, like k to infinity and 1 over x to the p, and if p is this and k is that, and I don't know why they don't do it, but okay. 20 minutes. Let's see how much I can get us into the next section. And I think I'll motivate it with this idea here. This was the integral I started class with, or not class, but I started this idea with last class, right? We already showed that that diverges, and it diverges from this as well, right? But we know that this diverges. Check. Now, and while you're thinking about that, I'm going to draw the graph of this function on the board here for us. The graph of 1 over x looks like this. That's f of x is 1 over x. We already found in this integral over here, we looked at the area from 1 to infinity And we said that that basically became infinite and diverged, right? That's what we said. And now what I'm doing is I'm asking you not to look there, but to look, well, that's the question, right? Now I'm asking you to look between 0 and 1 and look at that and determine what the area of that is. What's your instinct telling you? Diverge? Should it still be infinite? You think so? Yeah, we do get division by 0, right? I mean, we do, right? That's the difference. See, in the last problems, the problems from last time, this was what we call a type 1 improper integral because one of our limits of integration was infinite, right? That's one type of improper. The second type of improper is this. And here, these are not infinity, right? But we have a problem, don't we? Where's the problem? 0 can't be plugged in, right? We have an asymptote at 0. This is what we call a type 2 improper integral. See the difference between two? We have infinity on one of the limits here versus a discontinuity somewhere in the interval is a discontinuity of the function, right? That's type 2. I'll formalize this more later, but so I really wanted to know just like what your instinct was telling you as far as what you think the area should be, right? So from here, this area we already know is infinite, so divergent. And then here, I'm asking you to just make the conjecture if you think that's going to be infinite or is it going to converge?
I would think it would be divergent.
You think it's what?
Divergent.
You think it's going to do what this one does? You're going to do the same
No,
thing?
I just think it's not defined, so aren't those like
It's not
the same
defined.
parameter?
Yeah, okay, yes.
I think it has the same area as the red one plus the area of 1.
Okay, so you think that it's,
'Cause like
you think it's this area but a little bit more?
plus 1.
Yeah, plus 1, because so you're saying it's like this, like here, like that red, and then that part up there, those are the same, and so you have to add that area as well?
Yeah.
Yeah, okay. All right, well, there's enough, we can talk about it all day long. Let's figure out what it is, okay? Let's figure out what it is. So how do we attack these? What we do is this. You know how here we couldn't go to infinity, so we replaced it with t? And then we let t go to infinity? Here, we can't plug in 0, can we? But we can get close to 0, can't we? We can replace that with t and take a limit and let t go to 0, right? That's what we could do. So I'm going to go through this procedure the way that I do these problems. So I look at this, I start the problem, I look at it, right? I look at it, and I realize, oh shit. I go, you know, problem at x equals 0, right? I have a problem at x equals 0. And then what I do is I draw a number line. And I draw my interval, 0 to 1. And I'm looking here, right? This is where I'm interested in, this piece right here, right? From here to here. Yeah? So if I'm going to replace 0 with t, I'm going to want to let t go to 0, right? From which side of 0 do I need to come in from?
Right side.
The right side. I have to because I'm looking between 0 and 1, right? So if I'm going to approach t, if I'm only between 0 and 1, I must approach from the right side, like that. So when I write this limit down, it's important that I put the direction I'm approaching the 0 from. All right, let me just write it down. And this is our first example. This is kind of an informal introduction into type 2. I'm going to leave the picture there. So here's what we've got. I'm going to rewrite this as a limit. I'm going to let t go to 0 from the right because of that picture. And I'm replacing the 0 with t, right? So integral from t to 1 of 1 over x dx. Okay? Feel good? All right, now I'm going to just do the antiderivative. Limit t goes to 0 from the right. And the antiderivative of that is natural log of the absolute value of x. Right, that's our antiderivative. Do I need the absolute value? Do I?
No, because you're coming from positive.
I'm between 0 and 1, right? So I'm not plugging any negatives in, so I don't need the absolute value, all right?
Makes me happy.
Yeah, I'm going to leave it, but I don't need it, okay? And then what goes here? From where to where? T up to 1, right? Keep going. Limit. T goes to 0 from the right. And plug in. We're going to plug in now, right? Plug in 1, natural log of the absolute value, natural log of 1. And then over here, natural log of t. And the natural log of 1 is 0. We have to know that. Or get your calculator, but you should know that. And then now we need to figure out what happens to the natural log function as I approach 0 from the right. So you got to know what natural log looks like, which I'll put right here. This is what natural log looks like. So as you approach 0, here's 0. As you approach it from the right-hand side, where does it go? Negative infinity.
But you've got minus, so it's going to go to infinity.
So it's going to go positive. So it's negative infinity. Do y'all understand that? Trying to figure out what happens to the natural log function as I let that t value go to 0 from the right. So I'm looking at the natural log function. I'm saying what happens as I approach 0 from the right? My graph dives down to negative infinity. So what's our answer? It diverges, which is what we suspected it would do, right? From the geometry, you can see it. Like this is a nice way to see the symmetry of the problem, right? Okay, I still have a few minutes. We good? All right, let's try another one. Oh, diverges, sorry, diverges. What about this? Okay, so remember, what did I do last class? The first problem I did was the integral from 1 to infinity. Right, last class, I did the integral from 1 to infinity of 1 over x dx, and that diverged, right? I did the integral from 1 to infinity of 1 over x squared dx, and that converged, right?
Yes.
And then I just did the integral from 0 to 1 of 1 over x, and that diverged. And now I'm going to do the integral from 0 to 1 of 1 over x squared. And what do you think that's going to do? You what?
I don't want to assume.
Yeah, I don't want to assume.
Every time I do it,
Do you think we have the same sort of symmetry?
I hope so.
Yes and no, I'm hearing about. Let's just do it.
Yes.
Let's just do it. Let's see what happens. So I'm going to I'm going to look at this. I'm going to go, okay, hold on. I have a problem. Where's my problem? 0, right? I have a problem at 0. I have to see that. If I don't see that, I'm in trouble. You're in trouble. All right? So number line, here's 0, here's 1, because I'm going from 0 to 1. And I have to approach 0 from the right again, don't I? So I'm going to rewrite this. I'm going to go limit. T is going to approach 0 from the right. And I'm replacing the lower limit of integration with t, then to 1, and then 1 over x squared dx. Yeah? Then, the antiderivative. What is the antiderivative of this? Yeah. Negative x. So can I put negative 1 over x? Is that all right for the antiderivative? Not showing that work. That's the antiderivative of this. I'm evaluating from t to 1, right? T to 1, which is the limit as t goes to 0 from the right, and now I have two things being subtracted. Am I moving too fast? Is this all right? Okay? Too slow? So speed it up. Speed it up. Okay, let's plug in 1 first. Hey, that's not bad, right? 1 goes in there, no problem. Negative 1 over 1, negative 1. And then minus 1 over t, yeah. Replace the x with t. And now let's take a limit. What happens if I let t go to 0 from the right? So if I'm approaching 0 from the right, I'm plugging in numbers that are really, really small and positive, right? Really, really small and positive numbers. So imagine I take a really, really small positive number and I put it right here. 1 divided by a really, really small positive number would be, so I'm going to ignore that. So 1 over a really small positive number would be a really big positive number, and then negative negative would be positive. So this is becoming what? Infinite. Which means it diverged. Right? What are you confused about?
Okay, so.
Take the number 1 and divide it by t, but let t get really small. So let's, what's 1 divided by 1? 1? Okay, make that smaller. What's 1 divided by a tenth? 10, right? What's 1 divided by 1/100th? 100. The smaller the bottom gets, the bigger the ratio gets, right? So that becomes, forget these negatives. Okay, 1 over that should become infinitely big, right? And so we've got that. Which means it does what? Diverged. Was that the same thing that this one did? It's not. It's the opposite of what it did, right? It's the opposite. The integral from 1 to infinity of 1 over x squared dx, that converged, but we're seeing that if you go from 0 to 1, it diverges. So if we go look at the graph of this, here's 1 over x. That's the one we did before. That's 1 over x. How much time do I have? 5 minutes. Okay, so we said that the area, we said this area here, this is 1 over x. That area was infinite, and we said the area over here was also infinite, right? So that's for 1 over x. That's what we said. But now we just did a problem where we had a different function. It wasn't 1 over x. It was 1 over x squared, right? There's the graph of 1 over x squared. And what we're saying here is that this area here is convergent, and this area here was divergent. And you can see we don't have the same symmetry. Do y'all see we don't have the same symmetry? Do you see how this one tapers off like this? And if we draw this and eliminate that, just ignore that. Do y'all see that this is different than what's happening over here? Like how rapidly it's going down to 0 here, but there's more of a gap in here, and that makes a huge difference in terms of the area. Yes?
This is just a quick question.
Okay.
The limit of a constant is just a constant, right?
Yes.
Okay.
Yep. Okay. So let me tell you on your homework, I don't think you're ready to do all the type 2s yet, but I'll tell you for now, you should be able to handle now everything up through 22 on 6.6. So I would challenge you on 6.6, problems 5 through 22. These are all of these are type 1, which means you're going to have infinity or negative infinity on your limits. If you want to start working on the type 2, those are going to be problems 23 through 32. On your exam, what are we going to do? No type 2s on the exam. No type 2s. All right? Just type 1. A real easy type 2. I'll give you the one we just did.
Yes.
Yeah. Hey, so we're almost out of time. Our test is on Thursday, right?
Yeah.
So we still have Tuesday to talk about the test. Please study this weekend, use those reviews. I want to share something with you real quick. I was driving my daughter to school today, and normally she's not a procrastinator. She's really good, but she had to go to her friend's birthday party yesterday, so she didn't have time to finish her math homework with me. So she showed me the worksheet, and I don't know what the teacher was showing them, but the teacher had this like 0.3 repeated, and then it was like 0.7 repeated, then it was like 0.43 repeated, 0.719, all of that repeated, and the instructions were to convert these to fractions. So how do you convert a repeating decimal to a fraction? Do you have some?
Also, the first one's like 1/3.
1/3. Okay, but do you know the technique if you have a repeating fraction like this? How to convert it to like how to convert that to a fraction without doing any work? No? Okay, so it's real simple, and this is what they were showing her, is that whatever's repeating, you count the decimal places, right? So I have one decimal place, then it continues over, right? Here the repeating, it's one decimal place. This is two decimal places, and then the repeating continues. Here's three decimal places, and then the repeating continues, right? All you do is you take that number, and since it starts repeating in the first decimal, you divide it by 9. This one, you take 7, you divide it by 9. This one, you take 43, and you divide it by 99. Okay? This one, you take 719, and you divide by 999. If you don't believe it, get your calculator out, and you can check it, all right? So they were showing that to her, right? Yes?
Is that in the last decimal also like 71 over 99?
The last decimal?
1, 2, 3, 4.
The last two nines cancel.
What?
No? If it's not, then
It's
I'm
like not
sorry.
reducing.
No, I don't understand your question. I don't understand your question, that's all.
So is it how would you? What was the word? Sorry,
Reduce.
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 Oh yeah, well you don't cancel the 9s. No, you don't do that. But yeah, you could reduce these fractions. Like the first one was 1/3, right?
Yeah.
But here's my point. I want you to ask your teacher what this is.
No way.
What is it? 1.
That's
Right?
technically, like,
Because if you follow this method, you should take that number and divide it by what? 1/9. And that means you're saying it's 1. So I said, I want to see, tell me what your teacher, if she is convinced that these are the same numbers or not. Is 0.999 repeated the same number as 1?
It's the limit of
Yes.
No, I'm not saying that.
No, that's what I'm saying is the.
Are these the same numbers? Is 0.999 forever the number 1?
Yes.
Or are they different?
I mean, I don't think it technically is.
if you write.
Is there a number between these two numbers?
No.
There's no number between these two numbers. There's no number between. You cannot find a number between these two numbers, which means they are the same number. We can prove this later with series, but I don't. Oh, you know what? She told me that she's not going to see her teacher today. She's just turning that.